Okay, good morning, everybody. Welcome to the third week of semester. I hope you've all settled in and found ways to adapt and learn and enjoy in these new circumstances. Just as usual, a couple housekeeping notes before we get back to the flow of lecture. Just remember at some point today to click on the attendance sheet and sign yourself in. Hopefully you have all successfully completed deliverable 2, and I've embedded deliverable 3 for you to start working on today, which as usual will be due at 11:59 p.m. Tomorrow, Monday evening at 11:59 p.m. Any questions about the deliverables? I'm going to talk about deliverable 3 in a moment, but anything about procedure, how things work, office hours? So far, so good? You can all hear me okay? I'm sharing my screen. I've got my audio on. Please type in chat, you can hear me. Okay, everything's okay. Sometimes it's hard to tell. Okay, all right, so let's talk a little bit about deliverable 3, and I'll share it in a moment, but just to take a couple steps back, there are sort of 3 main moving pieces to your entire set of deliverables. Robert said he's having a WebSocket issue. I posted something to Teams this morning. One student found that their ad blocker was causing a problem. So I have got a couple of emails yesterday and this morning about issues about your computer recognizing the Leap Motion device after not using it for a few days. Have a look there. If that doesn't work, send me an email, and Amanda and I will try and help you with connection issues. Okay, so deliverables as a whole, 3 main moving pieces. You've kind of finished the first of the 3 pieces, which is obviously the visualization. As we talked about in the last 2 weeks, we want to establish this real-time feedback loop between the user and the device. They do something with the device, and they visually see the system respond in some way. You've been working on that. In deliverable 3, you're going to move on to the data side of this. We're going to have to collect, you're eventually going to collect, or I'm going to collect all of the data from all of you. You're all going to record Leap Motion data from your hands, and we will collect together a combined data set which contains 61 or 62 sets of hand data. That's the data part. And then the third part is the machine learning part. You're going to be eventually training a machine learner to recognize perhaps a new hand that comes into the field of view of the device and uses the 61 hands that have been seen previously to predict which of the 10 ASL digits is being signed by the new user. So in deliverable 3, you're going to be moving on from visualization to starting to manipulate data. And what you're going to be doing specifically in deliverable 3 is starting to record some data. So we've got this, here's the feedback loop that you've been establishing over the last 2 deliverables. You're going to be recording data, saving it out to a num.js, so this stands for numerical JavaScript. You're going to be saving it out to a data structure, and then you're going to be creating a separate playback JavaScript script in deliverable 3 that is able to read in that array and project it back on the screen for the user. So we're going to have record and playback. The way we're going to do this is you're going to now bring both of your hands into play, where, like before, we're going to draw your primary hand, and the moment that your secondary hand comes into field of view of the device is going to signal that it sees the second hand not by drawing the second hand, but by turning the hand red. And the moment that the secondary hand leaves the field of view again, your Leap Motion, your software is going to capture 1 frame of data. So why are we doing that? We're going to use this idea of bring the secondary hand into the field of view, take it out, and take a snapshot at just that moment, because we're going to need to capture clean data for your machine learner to work on. As you've probably seen, sometimes the Leap Motion device has a hard time seeing the hand, and there might be some jitter. So the idea is you can visually steady what's happening on the screen and then just quote-unquote snap a picture at exactly that point. I'll play this video again so you can see how this works. One hand recognized by the device, two hands recognized by the device, and the moment there's one again, it snaps a photo. You'll see the background actually flashes for a moment black. I'm not sure if that shows up on the feed here. Okay, so that's the idea. We're trying to capture clean data in this assignment, which will be used in deliverable 5 by your machine learner, and you're going to set up your machine learner in deliverable 4. So we're recording data, deliverable 3, building a machine learner in deliverable 4, and then combining the data and the machine learner in deliverable 5. That's where we're headed. Okay, a couple of notes about deliverable 3. We're going to start using the second. The second JavaScript library here, num.js. You're now hopefully pretty familiar with P5, which we're going to be using for all the visualizations. Num.js we're going to use to handle all of the data that you're going to be generating and manipulating in your deliverables. Num.js allows you to store data in a scalar, a vector, a matrix, or higher dimensional matrix known as a tensor. And I love this cartoon. This is a good way to remember the kinds of data structures that you're going to be manipulating in this assignment. As you can see, all of these names refer to the dimensionality of the data structure that is storing your information. We're going to be working with this guy over here, a 3-dimensional tensor, in your Leap Motion in deliverable 3. And we're going to do that in the following way. You're going to be creating a 3-dimensional tensor, which you see visualized on the left here. This tensor is, as you can see, it's got basically 6 matrices stacked together. This tensor has 5 rows corresponding to the 5 fingers. It has 4 columns, which correspond to the 4 bones in each hand. And if we walk from the front of this cube towards the back of the cube, you can see that it has 6 stacks, which correspond to the XYZ coordinate of the base of that bone and the X, Y, and Z coordinate of the tip of that bone. So for each of the 20 bones recorded during each frame, recorded by Leap Motion in each frame, those 20 bones, each bone has associated with it 6 numbers. So how many numbers in total are being stored in this tensor? Go ahead and type it into chat. Not quite. We've got 5 rows, 4 columns, and 6 stacks. So there are a total of 120 numbers that are stored in this tensor. So we're going to basically take, we're going to extract 120 numbers from a frame at the moment that the secondary hand leaves the device's field of view, and take all those 120 numbers and shove them into one num.js 3D tensor. And that's going to be the data structure that we save, and that's played back by your second JavaScript script. So you're going to have to get pretty familiar with manipulating num.js tensors in this deliverable. So I would recommend, you'll see this figure as you start to work your way through deliverable 3, but it's worth us spending a few moments talking about this. The first thing you'll be doing in this assignment is referencing subsets in this matrix. So basically extracting or pushing numbers into one part of this matrix. Just as a reminder, each row here corresponds to each finger. So the 0th row, the topmost row, is going to contain all the information about the 0th finger, which according to the Leap Motion device is the thumb. So that gives us a total of 4 times 6, or 24 numbers that are going to represent the orientation of the thumb. We can then take a subset of that, which is not just the first row, but we can take the the fourth column. And if we extract those 6 numbers, those correspond to exactly the 4th bone in the first finger, the tip of the thumb. And if we take a further subset of that, we can take X, Y, and Z. We take the 4th, 5th, and 6th number in the 4th, 5th, and 6th stack of the 4th column of the first row, and that gives us the X, Y, and Z coordinates of the tip of the last bone in the thumb. Okay, where in this matrix would I go if I want the 3rd bone from the 4th finger? Where would I go in this matrix to find the 3rd bone in the 4th finger? Let's say I want all 6 numbers that represent the orientation of the 3rd bone in the 4th finger. Where would that be located in this tensor? 3rd bone in the 4th finger. Four down would take us to the 4th row, exactly. And then 2 over would take us to the 3rd row, which corresponds to the 3rd bone, and then we would take all 6 of those numbers, exactly. So you'll learn in this deliverable about how to move through a num.js tensor and extract subsets of this tensor. You're going to be using 2 num.js functions pretty heavily, pick and slice. These are very different, and there's pointers to the documentation, but I wanted to just mention it here up front because I think it's worthwhile. Pick, if you pick a subset out of a tensor, it'll give you back a new tensor which is lower dimensional. So for example, if we look at panel A here, if I was to pick the entire top row, if I was to ask for that, I would get back a 2-dimensional tensor, otherwise known as a matrix. So I started with a 3D tensor here, or a 3rd rank tensor if you like, and I have a lower dimensional or a lower rank tensor. We went from 3D to 2D, that's pick. So we get back fewer numbers that are stored in a lower dimensional data structure. Same thing in B, we started with a 3-dimensional tensor, or a 3-rank tensor, and by picking this subset of it, we're getting a 1-dimensional tensor or a vector. You can go one step farther and ask for just one element in the tensor, and it'll give you back a 0-dimensional scalar. Okay. Slice, on the other hand, will also give you a subset, but it'll give you back a subset that is of the same dimension. So for example, we could slice this 3D tensor, for example, asking for the 2nd, 3rd, and 4th columns, and that would give us back this part of the tensor that I'm circling with the mouse. Hopefully you can see that. So it's giving, pick is still giving us back a 3D tensor, but just a smaller one. We have fewer, in this case, we have fewer rows. Alternatively, we could ask for the first 4 out of the 5 columns. We could slice that, and that would give us back, again, a 3D tensor, same dimension, but it has only 4 of the 5 rows. Smaller size, but same dimensionality. So pick and slice are slightly different. If you've ever worked with NumPy or the numerical Python library before, that's a little bit different, but it should sound somewhat familiar. So if you're familiar with NumPy, there's going to be some differences in num.js, so just be aware of that. If you've never seen NumPy or num.js before, spend some time in this deliverable getting familiar with how to manipulate scalars, vectors, matrices, and tensors in num.js. Okay. I think that's all I have to say about deliverable 3. Any questions about any of that before we move on?
I have a question.
Sure, go ahead.
Yeah, so about the 3D dimension that represent the hand, since the thumb doesn't have the first bone, do they have any information stored in the first column?
Yeah.
Or it will be just empty?
Yeah, that's a great question. So you can actually test that yourself. When you get to the point in deliverable 3 where you grab and fill up an entire tensor with one frame of data, you can reference the 0th bone in the 0th finger and look to see what is stored in there. What you will find is in those 6 numbers, which represent the X, Y, and Z base of the bone and the X, Y, Z of the tip of the bone, because the thumb metacarpal here is sort of simulated, it's not real, it's a point rather than a line, those 6 numbers, or those 2 sets of triplets, will be the same. They represent a line of 0 length, and those overlapping sets of X, Y, Z triples will represent the position of the green bone that you see here, the proximal phalange in the thumb. So that's a great question, and that's a good way to test your knowledge of what's being stored in this tensor and where. Good question, thank you. Any other questions before we move on? Okay. All right, so we are here in the lecture. We would have started in on design principles today. We're a little bit behind, but that's fine. We'll spend most of today talking about design as philosophy and process. Hopefully we will finish that up today and start in on lecture number 5 on design principles. This coming Thursday, I will not be lecturing. You will be having a guest lecturer. There's a PhD student in the Netherlands who is defending her PhD thesis, and I am the external examiner for her, and that's occurring at Thursday morning, our time. So I won't be here. One of my PhD students will be here and will be delivering the lecture on displaying visual information. Okay, so back to design as philosophy and process. And this was just a reminder here again of your fellow student Garrett Fauscher, who found that ad blocker sometimes causes a problem with leap motion. So I dropped this screenshot into Microsoft Teams. Those of you that are having errors reconnecting with your leap motion device, have a look and see if this helps. Otherwise, let Amanda and I know and we can try and help you with that. Okay, so just as a reminder last time, design in general, we're going to think of this as a process. We're translating some need, which may be well articulated or not so well articulated by a set of potential users. And we're going to try and pick a design process, some way of translating that need into a structure or process. Structure or process itself. So there may be many different ways to get from point A to point B. Which one you think is better than another reflects your design philosophy. We're going to look at a number of design philosophies and processes across different domains outside of HCI, starting with very subjective domains like fine arts and ending with HCI. So we're going from more subjective to more objective, because as you'll see over and over again in this class, HCI is trying to reconcile the beautiful and the subjective with the useful and utilitarian, helpful aspect, objective aspect of HCI. So let's start at the very subjective extreme, which is fine art. It's hard to talk about design principles here. We don't really design a work of art, but if we were to try and think about it as that, what are some of the design principles? What are some features of some of these examples from mostly Western art, or all Western art, that is a design principle? Someone sits down to create something that is beautiful and engaging. What are some of the rules of thumb? What are some of the things they try and incorporate into a piece of art as they create it or design it? If you have an idea, you can go ahead and type it into chat. Yep, Cole says the rule of thirds, exactly, a very old tradition in Western art. What are some other features that are represented in these representative works of art here. What are some things that an artist might try and do well? Okay, color, so thinking carefully about color. You can see obviously some of these use quite a bit of color, others minimize color. What are some other design principles at work here? So we're not talking about design process, how to go about painting a beautiful work of art, but design principles, the things that exist in that work. Lighting, perspective, that's the idea, exactly. So these are design principles. We've talked about design philosophy. We've talked about design process, the way to get from point A to point B. Design principles are sort of the things that you're trying to do, trying to build into the thing that you're creating. Any students of fine art here? What are some of the artistic periods that are represented here? Old, that's true. We have something from the medieval period here, the Baroque tradition, which was a design principle in the Baroque period, was to try and maximize ornamentation. That was stripped out mostly in modern art movements, which tried to simplify somehow. So Ethan mentions abstraction. Guernica is a great example represented here. So in some cases, in some periods of fine art, the idea was to maximize ornamentation. Other periods, it was to try and minimize these. So some design principles that were at work during certain periods of artistic expression were inverted or militated against in other periods. Okay, so Sarah O'Brien mentions function. What was the goal of the work? Now Sarah's starting to think like an HCI designer. What need is being met by fine works of art? Okay, here's just a few examples of my own. Again, some of you already mentioned this. I'm going to focus on maximizing ornamentation for a moment, because we're going to take one step now from the subjective extreme, where maybe subjective considerations are the only considerations. We're going to take one step towards objective design and land in information visualization, where clearly thinking carefully and creatively about what to present is still at work. But we are also trying to meet a particular goal here, which requires, which is a little bit more objective. Somebody might want to learn about relationships between health and wealth indicators in different countries. So coming back to the Gapminder example, which we've seen before, what are some of the design principles that are at work in good infographics? What are some of the rules of thumb that the designer has built in to meet the need to communicate a lot of information? Think about some of the design principles that we just talked about for fine art. Are some of them still at work here? So clarity, exactly. Should be the first one that sort of jumps out at you. Clear colors for different variables, right? So we might want a large amount of color separation so we can clearly see, for example, countries that represent different parts of the world. We might use similar shades of blue, for example, to represent different sub-Saharan African countries. So we might want to maximize the difference between colors and minimize differences between colors in other places to represent conceptual differences. So this idea of clarity or simplicity is probably one of the primary design principles at work in visual design, which has been described as maximizing the data to ink ratio, otherwise known as trying to minimize ornamentation, or otherwise known as trying to keep it simple. If you think about the data to ink ratio, this particular screenshot in Gapminder as a whole communicates a lot of data or a lot of information, but tries to do so with a minimum of clutter. So if you think about every colorized pixel in this image, it is hopefully doing some useful work. There is nothing there. There is no extraneous. There's no extraneous ornamentation in Gapminder and in and good infographics. That doesn't mean that we're minimizing the amount of ink. We're not trying to draw as little as possible. We're trying to draw just enough to communicate as much of the information as the user asks for. Okay, it's a great GIF that I found a few years back that represents this. So in this case, we're starting with a spreadsheet, and in this GIF, we're gradually removing ink to clarify what is being communicated here. Clearly, this is very important information that needs to be communicated. Okay, so in this GIF, you can see there's about 10 or 12 aspects of the visualization that are being removed to clarify information. You'll want to think about the same thing when you're creating your ASL educational game. Learning something is not always pleasant for everyone. It's easy to become frustrated or bored when you're learning something. How do you communicate visually with your user just what they need to see, or possibly hear? You could build some audio into your system if you like. Just enough information to help them do what they need to do, which is learn to sign successfully the first 10 ASL digits. Okay, so less is more, and it's often a black art that you learn through a lot of work in HCI about what aspect to remove to clarify what you're trying to present to the user. Okay, so let's take another step into a different domain, which also blends subjective and objective considerations. This one contains more objective considerations than visual design, because now we are building physical structures or buildings. So architecture is probably the closest conceptual cousin of HCI, because in architecture, like in HCI, we're trying to build things that are functional but at the same time beautiful or engaging somehow. People like to spend time in the building in the same way that a user will like to use your software. Here are two very different buildings. The two images on the right are showing the inside and outside of a particular building, and another building on the left here. What are these two buildings? Obviously, two very different kinds of buildings. St. Peter's Basilica in Rome. Yeah, what is the second one? David Matthews says CSAIL, the Computer Science and AI Lab at MIT. Yes, so the CSAIL is housed inside this building, but what is the building? So this is the Stata Center, which houses the very famous CSAIL AI lab at MIT, built by the famous architect Frank Gehry. You'll notice that the inside is very different from the outside. Why? What is the major difference between the outside and the inside? The inside has normal corners, right? So you notice there are a lot of right angles in the interior of the Stata Center, and that is true of most buildings. Of course, there is curvature as well. In the case of the Stata Center, there are relatively few right angles, or less right angles than you would expect in a normal building. So obviously on the outside, we maybe have a little bit more freedom to pursue subjective ideas or creativity, but we are more heavily constrained indoors. So this is the first time we started to talk about constraints. So obviously people want to do things in buildings, and they may want to do very different things in different buildings, but based on the physiology of humans or human crowds, that dictates directly or indirectly constraints on how we construct the indoors of buildings. What are some constraints, and how do they flow from consideration of how humans are, how humans move, how humans socialize? How does that dictate constraints for building indoor environments? We are clearly starting to change indoor environments at the moment, given the pandemic and changes in social interaction between people because of the pandemic. Bryce says we walk across floors, so obviously we can only access features as high as we can reach. Can only access features as high as we can reach. Okay, so assuming the humans are obviously on the floor, that might dictate what we put on walls for them to be able to reach them. What are some other constraints here? Look at the added constraints in the indoors, in the inside of the status center compared to the outside. Why right angles indoors? How does that derive from considerations of human anatomy or human behavior? So why flat floors? Why not uneven floor? People can walk across uneven floors. Office chairs with wheels, yep, possibly. Although we've been building buildings with flat floors for a long, long time, long before office chairs and actually wheels, possibly. Ease of access, so that's true these days. So as we think more carefully about diversity, that dictates how we build indoor and outdoor environments, but that is a very recent change in Western culture. Something about flat floors that's comfortable. Bryce says you can walk across flat floors without thinking about your steps. For most people operating in indoor environments, they don't want to have to pay attention to where they're going to place their foot next. They're focused on whatever they're trying to do in indoor environments. Socialize with others, walk up and down stairs, navigate from one room to the next. If you go hiking in a forest, having a flat floor is probably not something you would expect anyways, but you may be more willing in that particular activity to pay more attention to where you're placing your feet. In an indoor environment, for most people, it would be frustrating or not very acceptable to have to be considered consistently looking at the floor. Again, seems like kind of an obvious thing, maybe not so obvious in retrospect. Okay. Let's keep marching further towards more objective domains where considerations of utility or what the person needs to do becomes more important than subjective considerations. So now we move into the engineering disciplines, where in engineering disciplines, the main design principle, or maybe this is a process, if you like, a way of creating engineering artifacts, is to try and separate subfunctions within an artifact. So for example, when we're building a car, obviously we would like to have wheels that allow for smooth transport over flat terrain. That's the subfunction assigned to the substructure of a car, the wheel. An engine, a different structure, is responsible for a different subset of functions inside the car. It's meant to convert liquid fuel into kinetic energy and then into motion. Imagine instead we designed cars where they were made up of a whole bunch of modules, but module X partly helped with smooth transport and motion generation, and module Y also contributed to both of these two functions as well, but in a slightly different way. Here's the simplest example I could think of a modular engineering artifact. We have this system here, a bottle and can opener, and as the name implies, it has two separated functions. One part of it punctures and opens cans, and the other one pulls caps off of bottles. What is the single word that summarizes the design principle we're talking about right now? We've talked about it already when we talked about the parable of Tempus and Hora. What is the one word that summarizes the most important design principle in all of engineering? Utility, close. So we want to make something that is useful. Keep it simple. Yeah, that's also important. We're talking here about separating functions within the artifact. So in our bottle and can opener here, there isn't one part that kind of helps with cans and also kind of helps with bottles, and another part that also kind of does that. We have separated the two different functions to two different parts of the structure. What is that? What is the word that captures that separation of structure and function? Specialization. We're getting closer. Modularity, exactly. That's, if you want to go back to the previous slide deck and go through the parable of Tempest and Hora again, we want to try and emphasize modularity in engineering, and that will include in a moment software engineering. Why is modularity a good design principle? When the minute we mention good, we're now moving into design philosophy. So the design philosophy of modularity. Why is modularity good? It allows us to simplify the design process. For most of what you will be doing if you go and work in industry and software engineering or any branch of engineering is writing down a set of requirements before designing the software or the system itself. So the requirements are going to be usually a set of written specifications. The system should do X, should do Y, it should do Z in this amount of time. It should not do A, B, and C, and so on. If we come up with a modular design, we can then write down a set of functional requirements that are independent of one another. Let's go back to our bottle and can opener example over here. So if we think about what we want this thing to do, we might end up with two separate functional requirements. FR1, it should open cans, and FR2, it should open bottles. Those are separate. If they're separate, we might then be able to sit down and create sub-designs or design parameters. For example, we might be able to design one end of our eventual system that matches should open cans. So if FR1, or requirement should open cans, a design parameter associated with that functional requirement might be it should have a sharp point for puncturing can top. So we're starting to go now from the need to something that talks about the structure and function. There is also an assumption, even in this extremely simple device, about the need that it's fulfilling. Somebody has this bottle and can opener. There's some constraint that is built in here. So there's some consideration of what the user is not going to do with this. This device can open bottles, it can open cans, but it cannot. There's something about those two things that it cannot do based on the design that's been created here. We're assuming that someone who buys one of these wants to open cans sometimes and open bottles sometimes. There is another third assumption that's built in, even in the simple device, that is not always so obvious. Thomas, how does it, right? Typically someone doesn't want to open a can and a bottle at the same time. Now that Thomas has mentioned it, it might seem obvious, but it maybe not have been so obvious going in. And as we started to modularize the system and decide that we're going to connect these two substructures on the end of this device, we are building in a constraint. This system cannot do X, where X is open cans and bottles simultaneously. We're always vigilant for those unspoken assumptions. That may be perfectly fine. It's hard to think of a user who would want to open cans and bottles at the same time. But we have, if there are such users, we've excluded them from use. They cannot use this device for that need. Okay, so let's go now from engineering to software engineering, again getting very close to HCI now. Again, like in engineering in general, we still in software engineering, we usually want to try and boil down the needs of our demographic into a set of written requirements. The software system should do X, Y, and Z? What are some common rules of thumb when we go to take those requirements and tend to actually turn them into code? Again, if you take the sister class to this, which is software engineering, there are a large number of design principles that have been formulated over the years for how to quickly, efficiently turn requirements into code. One of my favorites is the design principle of iterating tightly and often, which means you cycle through coding, compiling, executing, and debugging as quickly as possible. One of the reasons I like this design principle so well is I learned what happens when you don't do this well. When I was doing my master's degree, we had at the end of the master's program 6 months to create our own master's project in code. One of my good friends at the time mapped out very carefully his 6 months. He was going to spend 3 months coding and then a couple of months debugging, which would give him a month at the end to improve the system. Imagine writing code for 3 months without compiling it. Unfortunately for my friend, he never finished his master's degree because he could never get anything to work. He still had hundreds of bugs by the time it was the end of the semester. So you've probably seen this iteration tightly and often at play in the deliverables. Some of you might be getting tired of committing hundreds of changes, committing hundreds of changes to your GitHub repo, but I promise you this is the way to make progress. So just as an example, I am definitely not a master coder, never was, but if I'm writing a simple piece of code to sum two numbers, I usually start with something like this, and when I run my code, I know what I should expect to see. Number 1, yep, that's what I meant to see. I'm going to add two things together, so let's add two things together, just make sure that works. I'm probably going to want to add different things together, so let's store them in a variable instead. So I try, when I'm coding, to not go more than a few seconds without try to go a few seconds without compiling, coding, and debugging. Here's an exception, as you can see right here. I'm spending a little bit too long. I should expect no change to my code. So far, so good. I have my function, so now I should be able to just use my function instead. Let's see, hopefully that still works. Okay, all right. So again, depending on your design philosophy, you may think that iterating tightly and often is a good way to go. We could argue whether that's a good design principle or not. But it is a design principle. There are many others. Another one is data hiding, so trying to hide the guts of your code away from the user interface. This will be particularly important in HCI. As someone is learning ASL, they don't know, and they probably don't care, and they don't want to know how your machine learning algorithm is doing what it does under the hood. Okay. In software engineering, you will also study a number of design processes, ways to go about converting requirements into code. Remember, design principles are just rules of thumb. Process is the actual transformation itself. The most famous and easily understood design process in software engineering is known as the Waterfall Model because it flows from one phase to the next, and you don't go on to the next phase until you've finished the current phase. So in the waterfall model, you squeeze your users as tightly as you can to extract every last requirement from them. Once you have as detailed a set of requirements as you can possibly extract from your users, only then do you move on to starting to design the system? What are going to be the major software and hardware components to support those requirements or to instantiate those requirements? Once you have a very detailed design, then and only then do you move on to starting to actually code this up. And at that point, you might start to use some of these design principles like iterating tightly and often and data hiding. Once you've debugged your code as best you can, then and only then do you expose your system to the users. Very, very simple, but very, very flawed, at least according to most modern software engineering practitioners. What is the flaw in the waterfall model? There are actually several flaws. Why might you not want to go about designing your ASL educational system in this way, for example? The process doesn't respond well to changes in requirements. Exactly. So any of you that have spent any time in industry or will spend any time in industry, you will find very quickly that users change their minds. What happens if users change their mind halfway through this process? Exactly. So we're not getting feedback from our users. Bryce says you don't get feedback iteratively. So maybe we want to, on a regular frequency, get feedback from our users. As Mario mentions, we can't move on until you finish one task. That's also important if you're working in a large software engineering firm, because you might have designers, implementers, testers, user interface people, public relations people, sales people. How do you keep everyone employed and busy at the same time if you have these different components? Yeah. So there are different design processes that have become much more popular in software engineering, collectively known as agile methods, which are kind of the opposite of the waterfall model. Those alternative methods are particularly useful when users can't well articulate what they want their system to do. Let's imagine that you sat down with a friend and said, hey, listen, I have this thing called a leap motion device. It can detect your hand floating in the air. I know you want to learn ASL. What should an ASL educational game do if we're going to assume that it can recognize your hand waving over the device? It seems unlikely that a typical user or potential user would be able to articulate very clearly exactly what your ASL educational system should do, because they don't know what ASL is. They don't know what some of the challenges are about learning to sign ASL dexterously. So they don't know much about the activity. They also don't know much about the technology. So you have the leap motion device. That's a constraint. You're going to have to use this piece of hardware. So there's a lot that is unspecified or unspecifiable until you start to do some user testing. So when we now get to HCI, or interactive systems design, this is HCI design if you like, we are still trying to create something that's useful. So like engineering in general, like software engineering in particular, the main design principle is still create something that a user can complete the desired function. So we're still going to have requirements, but we are now going to add an additional clause to the sentence, while at the same time we want to try and maximize certain global properties of the interactive system. There are many of these global properties that are important in HCI design. We're going to talk about 4 of them in the last half hour of today's lecture: accessibility, usability, acceptability, and engagement. Collectively, these global properties, which aren't strictly about the function itself, we want the system to do X. That's a functional requirement. We want the system to do X while at the same time also being accessible to lots of different people. Accessibility is a non-functional requirement. It's called a non-functional requirement because it's not direct, it has nothing to do directly with the functionality of the system itself. So you can think of these 4 here, and we'll talk about many more later, as non-functional requirements that sit on top of the set of functional requirements. This is what makes HCI in many cases more difficult than traditional software engineering. If you're working on the inside guts of a piece of code and that internal piece of code is never going to come into direct contact with your users, you're usually mostly focused on functional requirements. Non-functional requirements aren't that important. If you're an interface designer, you're working on exactly that part of the system that is in contact with the users, you may be spending most of your time thinking about this and assuming that functional requirements are being supplied by the internal parts of the code. How do you know, however, as the design process is unfolding, whether these global properties are being met? Much more difficult to know whether a non-functional requirement is being met than if a functional requirement is being met. If a functional requirement is open a can and you give that can opener to a person and they open a can, great, you know that it's working. If you give that can opener to 100 different people, it's going to take more effort to know how accessible it is. Did you choose the right set of 100 people? Are they sufficiently diverse along the dimensions of human diversity for what you want them to do? So in design processes, all design processes that you see in interactive systems design, it is definitely not the waterfall method. There is no start, there is no end. There is a lot of iteration back and forth, which is represented by the two-headed arrows here. And as Bryce mentioned, in HCI design, we are iteratively and as frequently as is humanly possible, obtaining feedback from our target demographic. So evaluation and user testing, this will be something we talk about quite a bit later in the course. This is front and center in HCI design. How to go about doing evaluation and user testing, this is an aspect of design philosophy in HCI. What is it that we are showing to our users, and what is it that we're getting back? Sometimes it's a prototype. That obviously makes sense. We have a partially implemented system and we show them that, and we gain some metrics. We get some measurements back from how our users interact with that prototype, and those metrics influence how we move on from there. We might try and write down written requirements, or we might represent requirements in a visual way. So instead of showing them a system, we show them our understanding of what we think the system should and shouldn't do, and get feedback in that way. We might show them a conceptual design, so we might do a storyboard of what this system would look like and how people would interact with it when it's ready to go. We might give them an empty shell of the system, a physical shell, if it's a physical artifact. So this is physical design. So I don't know if Leap Motion did this, but they might have actually created they might have gone about creating an actual box that's about the dimension, the size of the eventual Leap Motion device, given this to people and see whether they wave their hand over it if they pick it up. Very important, especially when we're talking about smartphones. We talked about ergonomics already. So you might give someone a dull object, which has no intelligence in it yet, to just get some sense of how people are going to literally manipulate it, what they think it's for, and so on. Okay, we'll come back to the design process next time. But for now, let's take these non-functional requirements and see how we might start to get at them in the design process. So let's start with accessibility. We talked about this kind of already. The easier way to think about accessibility is to invert it and think about exclusivity. Who is being excluded from using the technology? And most importantly, can we do some user testing to understand who is being unintentionally excluded from using the technology? Okay. Again, we try and think about unintentional exclusion, starting with more obvious types of exclusion and moving to less obvious types of exclusion. So we've talked about this before. Obviously, people come in all different shapes and sizes. That may affect how we build an automatic teller machine, a mouse, a joystick, things that people need to grip or touch or physically interact with. More difficult is conceptual exclusion. Remember that the human brain is a prediction machine. When somebody pushes against the world, as we talked about when we talked about John Dewey, action is first. They have a prediction about how the world or the interactive technology is going to push back. What if that system pushes back in an unexpected way? The user is then either surprised, possibly delighted if it's something that's new and interesting. Remember the example of the bow and arrow video game for the Nintendo video game. Or possibly that surprising pushback from the world or the system is surprising and becomes frustrating. My father is not a big fan of technology. I spent many hours, hundreds, if not thousands of hours, trying to teach him how to use simple applications on his desktop years ago. I'm sure lots of you have had wonderful experiences teaching parents and grandparents about how to use technology. It is difficult for them because they have a very different mental model of technology than you do. In the case of my father, the thing that was most difficult is trying to explain the difference between a slow and a fast double click, because obviously a slow double click actually means two separate single clicks, and a fast is obviously a double click. So for those of you that have a laptop that does distinguish between a single click and a double click, what is the time interval that separates two single clicks from a double click? How many milliseconds? You can actually look it up for different applications. So David Matthews says 200 milliseconds, 100 milliseconds, so about a tenth or 2/10 of a second. Possibly, that seems reasonable, right? Somewhere around there. If you were to tell that to someone who is trying to learn that there are two different things that you can do with clicking on a mouse, two single clicks or a double click, or a single click and a double click, telling them the time that the device uses to distinguish between those events is probably not going to be very useful. We have all learned that through lots and lots of experience with different kinds of technologies. We know instinctually on some systems to look for or to try and figure out, does this thing distinguish between a single and double click? We know how to explore the system to look to see whether that boundary is there. Most of that is unspoken and unwritten. How do you communicate that idea to someone who doesn't even know that there is such a conceptual distinction to begin with? These cause challenges and make it difficult for someone to build up a mental model of the system, especially when we get to the psychology module of this class. We're going to spend a lot of time talking about how people build mental models. Unless David cheated and actually looked up that number, David has a mental model of his system and was able to run that mental model in his head to sort of guess about how long it takes for a piece of software to distinguish between a single click and a double click. Okay, what are some of the aspects of design that can make it harder or easier for a user to build up a mental model of the system? Okay, David definitely did look it up now. What are some aspects of visual design or interfaces that you can think of, examples where it tried to give you a hint about how it works, how the system works, what's possible on the system? How do modern technologies or modern apps or modern software systems, how do they advertise their function, or how their function differs from previous versions of the technology or more familiar technology? You come into contact with an unfamiliar app or an unfamiliar device like the Leap Motion device. How does that system, how does the interface of that system help you build up a mental model of how it works? So a lot of apps will by default start up a tutorial. Most app developers have used over the years that most people want to get rid of the tutorial, and they will learn the system by interacting with it. As John Dewey said, they prefer not to sit back and passively digest a tutorial. They want to interact with the system and push against it in different ways to see how it works. But other people are more comfortable with a tutorial. So at least a lot of apps that are potentially different from other apps, they will start by asking in some way, either explicitly or implicitly, would you like to be walked through a tutorial? Yep. Menus, obviously, this one is kind of familiar. If you're using a new app, the first thing you might do is look in the upper left where you expect usually to see a menu, or I guess maybe in apps these days you might look in the upper right and look for the 3 horizontal bars. Something up in either of those 2 upper corners, there should be something that unfolds or opens that allows you to see more of what's possible. But these days, the default is usually it stays folded up in the corner, and there's some simple icon up there advertising that you can learn more if you head up there. If you work quite a bit with an app, you start to build up a mental model of where certain things are in the menu hierarchy. That process of knowing where, quote unquote, where things are in a system can be confused if the same thing can be found at different positions. So some of you may have had the experience where you buy a new smartphone and you want to know where to turn off the notification sounds. So if it's notifications about texts or calls, do you go to call or texts, or do you go to preferences and notifications? In some smartphone or some technologies, turning off a notification sound can be found in two different locations. Not always obvious where in a menu hierarchy that particular feature is, because it has to do with notifications about an event, like a call. So maybe you go into the call part of the menu, but it's also a notification, a sound, which usually implies something about preferences or settings. So maybe you go into preferences or settings. Okay. We need to obviously put people first. We talked about pact analysis last week. We don't want to economically exclude anyone. There was a famous historical example to try and, as the name implies, provide one laptop for every child on Earth. This is the OLPC project. This is has now closed down, but obviously laptops and computer technology in general were pretty expensive, which meant mostly people in Western countries or developed countries had access to this technology. The one laptop per child initiative led to eventually the ideas for very cheap laptops or minimal laptops like the Chromebook. We'll come back to that example in a moment. Cultural exclusion. This one is tricky, again, because based on people's culture, there may be unspoken and unwritten assumptions that they bring to bear when they interact with technologies. What inappropriate assumptions or predictions might someone make based on the fact that they're not coming from the dominant culture? They're not a native English speaker, for example. How will text analogies, visual analogies, auditory analogies be interpreted if your native tongue is not English, for example, or if you're not raised in a Western country? Social exclusion, again, if we're developing technology that's going to be used by many people in the same place at the same time, maybe depending on how that social interaction works, the technology may not be available at the right time or the right place, depending on the activity. If it's spiky, so if there's certain periods during which that technology experiences heavy use, maybe too many people need access to too few computers or too little bandwidth at the same time. Okay, so let's have a look at Sugar. This was the original operating system for the one laptop per child project. So the laptop itself was called the XO. You can see that people were represented as X's and O's. Very, very cheap laptop. And they tried to create a very, very simple user interface, which is Sugar here. You'll notice, with the exceptions of My Neighborhood here, there is no English text on the screen. The idea was to try and get as many of these laptops into the hands of young children in developing countries as much as possible. Let's assume that you're a young child and you live in a very small village in South America somewhere, where you're surrounded mostly by jungle. You come from a terrain, an environment that is mostly jungle. You have never seen a laptop before. Obviously these days, even if you're a small child in a developing country in a rural setting, you've probably seen a smartphone before. So imagine at the time of OLPC, smartphones were not very prevalent. Somebody places this weird box into your hands, and on this box you see this picture. What do these three icons mean to you? A small child in a rural village in South America, where most of your physical environment is jungle. What do these icons mean to you? So the Wi-Fi tower here, which is clearly sending out a Wi-Fi signal, as Henry mentions, for a lot of children, they interpreted this as volcano, and the idea should be if you move your screen and this thing moves relative on the screen, you should be moving away from this thing, not towards this thing, where the design intent of this icon was to represent something that you wanted to move towards so you could connect your device to your friend's device and so on. And had the opposite and very unfortunate experience of being culturally exclusive, right? This is something that could only be interpreted by someone from the Western world and someone who has a lot of experience already with technology. Joseph says the paintbrush over here, which obviously we all know is a paintbrush and a palette, could be represented as a broom. Yep. Yeah, hard to know exactly what this is. Yeah, I think actually broom is a good example. What about this one over here on the lower right? What would this mean to a small child from a rural village in South America? Maybe this one is correct, maybe a board game. Of course, in the West, this is derived from chess and checkers, but there are a lot of grid-based board games in many different cultures, so maybe this one wasn't too hard. Okay. Let's move on to usability. So accessibility or exclusivity is about who can use and who can't use the technology. Usability is about how well they can use the technology. So it's now no longer a binary thing, accessible or not. It's usable. How well is it? How well can you use it? Shackle, who was an early innovator in HCI, described usability as it should be easy to use, easy to learn, flexible, and engenders a good attitude in people. I dislike this sentence because it is just as vague as the single word usability. One of the most difficult challenges in HCI is to take very seemingly obvious but vague terms like make your system accessible, make it usable, make it acceptable, make it engaging, and gradually unpacking that into much more specific language that is measurable. How do we know how easy a system is to learn? What measurements might you take during a user interaction with your system to defend your claim that your system is easy to learn? So we're going to take usability and unpack it in a different way. We're going to unpack it into, again, some terms which are hopefully slightly less vague. One aspect of usability is efficiency. People will get activities done with a reasonable amount of effort, and it is implied here in a reasonable amount of time. You can probably start to think about measurements that you could apply to measure efficiency. Hopefully a little bit more than you could think about measurements of usability. When you have your ASL educational game and you put your alpha testers in front of it, can you measure efficiency? How long it takes them or how much effort it takes them to learn the first 3 of the 10 ASL digits, for example. Effectiveness, how effective is it? Does it contain appropriate functions and content organized appropriately? So again, what does this actually mean? And this one, maybe you could measure it, but it takes a little bit of thinking about how would you know whether people find what they expect to find in the right places at the right time? That's the system is effective. How do we know whether a system is learnable or memorable? So how would we measure something? If you have a user that's interacting with your system, how would we know whether your system is learnable or memorable? This is different from whether the ASL signs themselves are learnable. That you have no control over. There are 10 different ASL signs corresponding to the 10 digits. Maybe a different set of 10 hand gestures could have been chosen that would have been more learnable or more memorable for users. What we're talking about here is not the ASL signs themselves, but your ASL educational game. Have a tester use the system again later. So as the HCI design process tells us, we're going to do iterative user testing. If something is learnable or memorable, what would you expect to see the second or nth time that you conduct testing with the same user? What should change from one round of testing to the next? We're getting now into measurement. What are the actual things that you would measure during those series of interactions to collect data that would defend your claim that your system is learnable or memorable? Change in response for the same input. Okay, so we're going to expose the user to the same input during multiple rounds of interaction, but what change are we looking for? Change of what? You'll note that we're trying to be more and more specific here as we go. They take less time to do things, absolutely, right? So if they learn the system, they know where certain things are and they don't need to go searching for them. If they remember things, they may be able to skip over certain steps, like for example, skipping over the initial tutorial. So the effectiveness or the efficiency may actually increase over a series of testing rounds with the same set of users, and that indirectly will indicate whether they learn or remember the system. Safety, this one is kind of more objective. This one maybe you could clump in with this one is kind of hopefully mostly obvious. The last one, not so obvious. This is the idea of utility, which is, imagine that the user is at point A and they would like to get to point B, which is the thing they want to do. The technology, however, doesn't go exactly to B, it goes to B prime. It lets them get to an endpoint that's almost what they wanted, but not quite. If you think of these as two vectors, we have A where they start, and B where they would like to end up, and B prime where your technology guides them. You could think about the angle between these two vectors as utility. The smaller this angle is, the greater the utility of your system. Most of you would like to get from point A to point B in terms of signing up for classes. At a certain day, at a certain time, you'd like to do so immediately and have it done with. But my understanding is that's not always the case. How does some of UVM's software deflect you away from how you would like to go about signing up for classes? What is some evidence of the lowered utility of signing up for classes? It crashes, okay? We expect these days, we have high expectations for software. It should never crash. So if it crashes, that means that you usually need to start again, or whatever the process is. You have to go back to zero and start out again. So most of you, as you sign up for classes, don't want loops, right? You don't want to have to start over again. The registration website turns off from midnight to 5:30 a.m. I did not know that. There you go. All right. Some of you are night owls, and maybe you'd like to do this late at night. Okay. I am sure if I gave you more time, you could think of plenty of examples of this. I think we only have 2 minutes left, so instead of moving on, I think we will pause here. You can't use the lookup courses to add button to add courses. That's true. Waiting lists for classes, I know that's not implemented very well. I usually do that by hand for my classes. Let's pause here for today. Just a reminder, you have a quiz due at 11:59 p.m. Tonight. Please do get started on deliverable 3 as soon as possible. It is somewhat lengthy, maybe about as long or a little bit longer than deliverable 2. I will not be here on Thursday. You have a guest lecturer who will be coming, and since we didn't finish 4, they will be continuing on with Lecture 4 and guiding you into Lecture 5 on design principles. Okay, have a good rest of your day, and I will see you back here next Tuesday. Thanks very much, everybody.